Everyone, welcome to the first Freshwater Stewardship Community webinar of 2025. This is actually our fifth year of running the program, and so we're so excited to have you for our inaugural one of 2025. We're thankful to have Alex Cadel here from the Nova Scotia Environment and Climate Change CLIMAtlantic program here with us today as our keynote speaker. My name is Monica Seidel. I'm the Communications and Fundraising Manager at Watersheds Canada, and I will be hosting today's webinar. Also have some staff members who are in the back wings. Ty and Mel are here to help everyone with their tech needs. So if you're having any problems with that, you can reach out to either of them, or you can also send messages in the group chat to ask any questions you have for today's session. We will have a dedicated Q&A at the end of today's presentation, so be sure to put those in the chat so that Alex can answer them. For those of you who may not be familiar with Watersheds Canada, we're a national nonprofit and charitable organization headquartered in Eastern Ontario. We deliver different freshwater stewardship and restoration programs across Canada by working with different community partners. So we have a couple of examples on the screen here. In our top left photo, we have a shoreline planting that was done with a college program. And so this was in order to restore the shoreline with native plants. And so all of these college students were out there as part of their coursework. We also have a photo down here on the bottom left, which was actually just from last week, working with a lake association and First Nations community to restore a walleye spawning bed. And so you can see the rock is being laid out by volunteers with rakes and shovels and bringing the rocks out by ATV. And so this is 17 tons of rock being put out on the ice, which will eventually fall into place over the spawning bed with the spring ice melt. And then we also do some direct education programming with children through schools and public libraries especially. And so this is from our nature discovery workshop with Buffalo Lake Métis Settlement in Alberta. As a national charity, we rely on these amazing community partners to be able to deliver our programs, but also from donor support from individuals. And so we would like to remind everyone that you have until the end of February to donate to Watersheds Canada, but actually claim that donation for your 2024 tax receipt. So if you would like to support some of the programming that I just talked about that's delivered across Canada to benefit Canada's lakes, rivers, and shorelines, you can do so by going to watersheds.ca/donate. A couple of things that I'd like to quickly draw people's attention to based on the time of year and something that might be of interest to you. The first is our Road Salt Education Toolkit, which is a free resource on the Watersheds Canada website by going to watersheds.ca/salts. This toolkit goes over a number of different resources and scientific literature around the impacts of road salts on our freshwater ecosystems. And so you can access a policy review, sample slide deck, blogs, and information graphics, which you can use freely to talk to your municipality, community groups, or just your family and friends, and learn more about the issue of road salt with our freshwater ecosystems. Upcoming event that we have in just about 3 months' time is the Watersheds Canada National Conference, which is happening in Haliburton, Ontario. This will take place May 1st and 2nd and will be a hands-on experience for people to take practical steps back to their communities to protect their freshwater areas. We just released the agenda a little while ago, and some of our confirmed speakers and sort of the layout of the conference have now been put up online. And so you can access the agenda and buy your tickets by going to watersheds.ca/conference. We have a number of great guest speakers who are leading different plenary sessions and also outdoor interactive demonstrations. So I would encourage you to visit watersheds.ca/conference to learn about all of that. If you are an online-oriented person, you're on the major social media platforms, you'd like to connect with Watersheds Canada and learn more about our programmings, find ways to get involved, volunteer, you can find us on Facebook, Instagram, Twitter, LinkedIn, YouTube, and Blue Sky. And so all of the handles are on the screen. Ty is also going to be putting those in the chat, so you can pick whichever one is your favorite and follow us there. And we also have our main info line there, info@watersheds.ca. So if you have any questions after today's session or want to learn more about our programs, you can reach out to me through that. And we just encourage you to stay connected even after today's presentation. We will be sending out a couple of different resources after today's presentation, so if you have to leave a bit early, that's no problem. We are recording today's session, and we also will be providing an education handout summary of today's presentation, which you can use to bring to other team members or community members that you think would like to learn about what was covered in today's presentation. So the program that we're all here for today is the Freshwater Stewardship Community. As I mentioned, we are in our 5th year. Today is actually our 50th webinar, which is pretty crazy. And we have all of these webinars and the handouts that go along with them posted for free on our website. So the page that you would have gone to register for today's session, if you just scroll down that page a bit further, you'll find different category headings, and you can access a number of different free resources from expert speakers. And we also want to make sure that we recognize the different foundations that make our freshwater stewardship community programming possible for 2025, supporting a number of different initiatives under that umbrella, but also the webinar series that we'll be hosting this winter. So thank you to the Echo Foundation, Hodgson Family Foundation, Peterborough KM Hunter Charitable Foundation, and SM Blair Family Foundation. When you join an online community, it can sometimes feel like you just show up for a webinar and you don't really know who else is there. So we always like to tell people that you are a part of a really large community across the world. Obviously, we have a big skew for Canada and the States with our viewership, but we do have people from 23 different countries who are a part of this community. And since 2021, we have reached over 12,000 people with our different resources. As I mentioned, those different menus that you'll find at the bottom of the Freshwater Stewardship Community page, everything's kind of grouped into different buckets. And so you can find a topic that is of particular interest to you and then find free webinars and handouts related to that. Finally, I just want to make sure people know about an upcoming webinar that we have happening on March 6th. So this will be about a farm stewardship collaborative that Watersheds Canada is actually a part of. And so we'll have some different guest speakers from Ducks Unlimited Canada, as well as the founder of the East Central Farm Stewardship Collaborative. And so this will be talking all about the importance of community organizing, coming together as different organizations and individuals to lead different stewardship action. And so you can go to watersheds.ca/freshwater-stewardship to register for that webinar. And so I will now introduce our speaker. So Alex works for the Province of Nova Scotia, supporting the delivery of climate services in Nova Scotia in partnership with CLIMAtlantic. His work helps governments, organizations, and individuals understand climate change information so that they can make informed decisions about how to respond and adapt. Alex holds a Master of Climate Change from the University of Waterloo and a B.Sc in Environmental Sciences from the University of Guelph. He resides on unceded Mi'kmaq territory in Dartmouth. So Alex, I will pass everything over to you.
Fantastic. Let me share my screen on this end here. Make sure that's coming through okay. Yep. Wonderful. Well, thank you, Monica, for the introduction, and of course to Watersheds Canada for the invitation to be part of the webinar series. Exciting that this is number 50 for you already. We thought that an interesting topic for today would be to take a bit of a deep dive into how to find, understand, use, and communicate some of the latest climate change data for some of the work that you're all doing around water resources. And in terms of why that seemed like a good idea, I feel like I've seen quite a few instances recently of people not knowing whether they could be using climate data in their work or how to start using climate data if they were interested in what data sets they could access, or not quite understanding climate data well enough to use it effectively or communicate it appropriately, things like that. And first of all, I'll say that's all completely reasonable. I know this can get challenging in certain ways. There's a lot of complexity to the topic, but I think that together we can do better and we can all try to be a bit more confident and accurate and clear in how we're using and communicating climate information. So really that's the goal for today is try to increase your comfort level with using climate data in water resources work, whatever your past experience might be. So I've tried to select a flavor of relatively basic to more advanced questions. Hopefully there's something here for everybody. Limiting ourselves to talking about precipitation, not because it's the only thing of importance, but just to keep it simple here. And I'll mention as well, as Monica mentioned in my introduction here, my focus, I work in Nova Scotia, my focus is there. So some of the specific data I'll be referencing is using examples from the place where I work. But I think the general process and some of the insights here should be helpful for everyone, no matter where you're located across the country. So that being said, I'm trying to be somewhat ambitious here and cover 6 different things, at least in a brief way, in our time together this afternoon. First, I just wanted to briefly touch on CLIMAtlantic, so those of you that don't know anything about the organization have a better sense of who we are. Second, we'll touch on some key concepts related to just understanding climate data. Third, we'll talk about where to find some of that information. Fourth, we'll do a bit of a deeper dive into some precipitation-related variables and talk about some insights we can glean from the latest information. Fifth, we'll talk a little bit about some IDF curves. I know there's a lot of interest in extreme precipitation specifically, so we'll dig into that a little bit. And then finally, we'll spend just a couple minutes talking about choosing appropriate climate data for the purpose in mind. So we'll get right started here with talking about CLIMAtlantic. As mentioned, if you're not familiar with the organization, we are the climate services hub for Atlantic Canada. So really what that means is we're an independent expert voice on everything related to climate change impacts and adaptation. So we're here to provide free, publicly accessible support to governments, to communities, all types of organizations and researchers and individuals, anyone who's trying to consider climate change impacts in their decisions. We're here as a easily accessible way to get your questions answered, or at least be pointed in the right direction for increased level of support. And we do that through providing guidance in accessing and understanding climate change data, connecting people with resources and expertise across the region, developing and sharing climate adaptation tools. For example, we have a coastal adaptation toolkit that folks are finding very useful. We deliver training, we do a variety of communications and engagement work, a whole bunch of stuff of that nature. If you're in Atlantic Canada and haven't connected with us previously, I would certainly encourage you to reach out. We'd be happy to chat. Or at the very least, feel free to check out our website, which is climatlantic.ca, or sign up for our monthly newsletter there, just to keep apprised of what we're up to. And I'll mention as well, we are the Atlantic Regional Hub for climate services, but if you're located elsewhere across the country, there are a variety of other similar regional climate services hubs that you might be interested in connecting with, whether that's Oranos in Quebec, Orca in Ontario, Climate West in the Prairie provinces, or the Pacific Climate Impacts Consortium on the West Coast. And all of us as organizations are connected at the national level with the Canadian Centre for Climate Services, which is part of Environment and Climate Change Canada. So wherever you're located in the country, there is support available for understanding some of this information. So if anything I'm talking about today sounds interesting and you want support for going further, please don't hesitate to reach out to CLIMAtlantic as an organization if you're in Atlantic Canada or some of those other ones mentioned. We're here to help. So from there, let's get right into some key concepts here related to climate change and climate data. And this is not intended to be a comprehensive look at climate modeling. I really wanted to focus today more on how we can use climate model outputs in practice. I think that's kind of reflective of where most people are in their work. But I think to do that, we should have a bit of a brief introduction or review of some key ideas just to ensure we're all on the same page. So I'll talk just briefly here about weather and climate. I'll talk about climate modeling, a little bit about CMIP and uncertainty before we get into some of the actual data pieces here. So to start with, weather and climate. Very key idea to start with. I'm sure all of us are familiar with the idea of weather, and certainly we were just chatting about this before you all joined the call in terms of the storm on the way tomorrow. Weather reflects our short-term changes in the atmosphere, and we know that these are often very chaotic, very difficult to predict, even several days ahead of time. Starts to introduce a fair amount of uncertainty, but often it's really the weather that is really impactful for our day-to-day decision making. We want to know exactly what the temperature is going to be like outside, exactly how much rain we're getting, where and when. These things are really important for that sort of very small scale decision making. When I'm talking about climate information, on the other hand, we're looking at patterns of weather over time. Looking at the long-term averages, typically at least 30 years worth of information, because that's enough data to give us a sense of what types of weather are typical statistically within a certain area over that period of time. And the climate is really about helping us understand the range of typical weather. And just to briefly mention one analogy that folks seem to enjoy here, we can think about weather and climate as a person walking their dog. I don't know if you've ever walked a dog before, but if it's anything like mine, it's certainly not walking anywhere in a nice straight line. It's darting back and forth across the path pretty chaotically, to the point where if I asked you to predict where exactly that dog was going to be at some point in the future, that's really difficult to do. So the dog in this analogy is representing our weather. If we focused our attention instead at the person walking the dog, our climate in this analogy, that tends to be taking a much more predictable trajectory. So even if we can't pinpoint exactly what the weather is going to look like at some indeterminate point decades in the future, if we look at some of the climate information and sort of run the long-term statistics, we can at least get a reasonably constrained understanding of the place where that weather is likely to be in, and try and build a bit of an understanding that way. So useful to keep that distinction in mind as I'm talking about climate data going forward. From there, just a few background pieces here on climate modeling. So if we're talking about climate model data, we should know what a climate model is. And really simply, this is just a computer simulation of Earth's climate system. We know that the climate is affected by many elements, from latitude to topography, ocean currents, wind direction, vegetation, all of these various factors. So a climate model is an attempt to represent the climate system, all of those different ways, to look at how energy and matter are moving and interacting between the atmosphere, the ocean, and our land systems. And of course, we don't just have one climate model, we have many, because there's a whole variety of climate modeling groups around the world that have used slightly different methods for simulating the really complex nature of our climate system. Each of these models is unique. They're sophisticated representations of the climate system. They have their own strengths and weaknesses. There's no best model. So this is where a multi-model ensemble comes in, where we're looking at grouped results from that multitude of climate models running the same experiment, because that really just allows us to capture, where do the bulk of model results fall for the same conditions, show how well models agree for specific values and how much they differ. And then finally, we have the idea of scenarios, which are really built on the idea that it's not possible to predict exactly what humans will do in the future in terms of our greenhouse gas emissions, for example. So emission scenarios are descriptions of future greenhouse gas emissions, as well as other factors, things like land use change, that might influence the climate. And by using different emission scenarios that have different assumptions, we can explore different what-if questions about ask those questions and understand the implications for its climate. So each of these scenarios represents a different possible future under a specific set of assumptions. They're not predictions of what's likely to happen, but they're useful descriptions of what a plausible future could look like under the conditions in each of those scenarios. And I'll introduce a couple specific scenarios as we get a little bit further in and start looking at data. Another concept here is looking at sort of the generation of climate model information. So if you're starting to look at climate data, you might quickly come across this term CMIP, or Coupled Model Intercomparison Project. So useful just to briefly understand what that is. And really, it's just a coordinated set of simulations by climate modeling groups, because as we're asking all these what-if questions, it's useful if all these groups around the world are asking the same questions so that we can compare their results to each other. That's just a helpful way to sort of approach this whole problem. So helpfully, the CMIP experiments, and there are other types of MIPs, but the CMIP experiments are used to inform the Intergovernmental Panel on Climate Change, or IPCC, assessment reports that come out periodically. So for example, CMIP 5 was our set of modeling experiments that informed the IPCC fifth assessment report from around 2013. And CMIP 6 is the latest generation currently that informed the IPCC's sixth assessment report that came out around 2021. And I mentioned those two specifically because they are the last two generations of climate model data we have available. They're both sort of in wide use at this point in time, so it's useful to sort of understand the difference between them. So really, when we're looking at CMIP 6 compared to CMIP 5, useful to understand that with all of the work going into climate models around the world, those models tend to improve over time. There's additional research that's being incorporated, additional refinements that are being made. So our CMIP 6 models tend to be a little bit more complex. They might have slightly better spatial resolution. They might represent small scale processes, things like cloud formation, for example, in a bit more detail. So that's one useful piece of this. And then, of course, with our latest data, our CMIP 6 data, the scenarios have also been updated. So with CMIP 5, we had a set of emission scenarios called representative concentration pathways, or RCPs, that perhaps you're familiar with. And in CMIP 6, we use an enhanced set of emission scenarios that build, oh, sorry, excuse me, going back a slide. There we go. With CMIP 6, we're using a enhanced set of scenarios that build on those called shared socioeconomic pathways, or SSPs. And really developing new scenarios over time is a normal part of studying climate change because with updated scenarios, we can incorporate new information about the real world. For example, what emissions did we actually see globally, as well as new insights about possibilities for the future. And then finally here, just wanted to mention a few words about uncertainty. This is a really interesting concept to dig into in terms of the sources of where that uncertainty is coming from. And usually we talk about three sources of uncertainty over time. One being internal variability within the climate system. So that is just the fact that we know from year to year, our weather patterns are a little bit different. Some years are hotter or colder than others. Some years are wetter or drier. And that's a reflection of some of the internal dynamics in our climate system that make it so it's difficult to predict exactly what will happen at some year in the future. The second major source of uncertainty is around models. So are they actually representing all of the processes they need to? Are there things missing? Are they agreeing with each other? That sort of thing. That's our model uncertainty. And then our final major source of uncertainty is around scenarios. So that's what I was saying about we don't know exactly what humans are going to do in the future. So that certainly drives some uncertainty into the future as well. And the reason I'm particularly spending time on this when we're thinking about water resources work and thinking about precipitation data specifically is that the sources of uncertainty specifically around precipitation tend to be a little bit different than for things like temperature. So that's what I'm trying to show on the graph here. These charts are from a study that came out a few years ago, and they're breaking down the fraction of total variance by those three different sources of uncertainty. On left, we're looking at an air temperature example. On the right, we're looking at a precipitation example. So starting on the left-hand side there with the air temperature, the axis is going from 2000 to 2100. We can see that in the very near future, the uncertainty is really driven by internal variability in the climate system. We don't know if in a few years from now it'll be an El Nino year or a La Nina year. We don't know if there's going to be a volcanic eruption. All of these little internal variations are really important for that immediate future. As we move towards the middle of the century, in that graph, we can start to see that model uncertainty growing in importance, where again, we're sort of smoothing out the internal variability by simulating a longer period of time, but we're not exactly sure if the models are capturing everything that they need to. And then as we move towards the end of the century, it's really the scenario uncertainty, that green chunk that really grows to be really dominant. Because when we're looking at temperature, it's really important to know whether we're going to follow a low emissions future or a high emissions future in terms of where we end up towards the end of the century, things like that. So I say that as context for the precipitation side, which is on the right-hand side of this slide, where we can see a bit of a different picture. It starts similarly, where we're looking at internal variability is really dominant, where, again, we don't know exactly if next year is going to be wetter or drier than the year we just had, and so on for the decades to come. But that really continues to be the dominant source of uncertainty all the way to the end of the century. So really what this means is when we're considering climate models and emission scenarios, that's really important when we're looking at precipitation and trying to tease out some of the underlying trends. But that's a little trickier to do with something that's very discrete like precipitation, because that natural internal variability is such a strong source of uncertainty, where year to year it's just changing so much that we really need to try and account for that. And it takes a long time to start to see other sources of uncertainty dominate. So useful to keep that piece in mind as well. So there's your little climate science 101 for today. Let's shift gears a little bit and start talking about where to find some actual climate data if you're interested in using some of this information for your work. So the good news here is that finding scientifically sound, locally relevant climate data is as easy as it has ever been. There's a ton of freely accessible information from various sources, all of which might be appropriate for different purposes, depending on what you're trying to do. One place that I suggest people start if they don't have a particular question in mind is looking at the suite of data portals from the Canadian Centre for Climate Services. These are all maintained federally, have a lot of good information on them. Looking at the one on the left here, just to sort of introduce this, is the Climate Atlas of Canada. It's a great place to start learning about climate change through mapping and storytelling, some really interesting sort of visual resources there. If we move right over to the right, we have PAVIX, which is advanced tools for users in academia, climate scenario developers, things like that, really expert users that are sort of used to operating in a programming environment. That tool is available. But the one I'm going to be talking about today, where I'm pulling some information from, is the one in the middle here, which is climatedata.ca, which I think is a pretty fantastic general source to start from. It's a really helpful entry point for generating useful insights from readily available data. I've done some minimal things with doing some simple calculations in spreadsheets, but nothing more complex than that. And a ton of information is sort of accessible there as a starting point. So if you've never looked at climate data before and want to start exploring it, that's my usual recommended starting point. And we'll talk about why for just a slide or two here. Uh, I'm not going to do a full demo of the site, but just wanted to briefly touch on some of the functionality that might be of interest if you're wanting to use climate data in your work. Some things you can do through climatedata.ca include exploring map views of different variables. You can look at gridded data, census subdivision data, watershed or health region data. You can look at absolute changes, or look at absolute values versus delta values, so the changes. You have access to both of those generations of climate modeling data that I mentioned, the CMIP 5 as well as the more recent CMIP 6. You can look at annual, seasonal, monthly values. We can change scenarios for a whole range of temperature, precipitation indices, plus things like sea level rise, rainfall IDF data, climate normals, future building design values. There's just a ton of stuff in there that can inform a whole variety of different implications. There's also information here broken down by sector. Right now, that includes transportation, agriculture, health, and buildings. More might be added over time. And each of those include context. They include case studies, blog posts, resources, links to related variables and why they're important, all that sort of thing. In the analyze and download menus, you can do custom index calculations for both climate projections and historical observations. You can do custom downloads for those data sets, things like that. There's apps on this site to look at spatial analogs. So, for example, if I'm looking at Halifax's climate for the middle of the century, I can look at what cities around North America have that climate now. There's a fire weather projections app that was recently added that has some great information. There's an amazing learning zone on here for diving deeper into some of the concepts that I've briefly touched on here today. And as mentioned as well, they have their own help desk. So if anything here sounds interesting and you want to access professional support to learn more, you can access that there. So for all of those reasons, I think this is a fantastic place to start, and it's where I've pulled some of the information, all of the information that I'm talking about today, just so you know where some of this is coming from. Just briefly, one more slide on climatedata.ca showing sort of a typical chart that you might get clicking on a grid cell for a variable like total precipitation, which is what's being shown here. I just wanted to point out a few things in chart format that I'll talk about in sort of a data grid format in the coming slides, just so you can sort of interpret them visually if this makes more sense to you. So I know this is a very small axis here, but this runs from 1950 to 2100 along the horizontal axis. So in the gray towards the left-hand side, we can see that is our modeled historical data. The shaded range represents sort of the 10th to 90th percentile. The solid line represents the median. And towards the right, we have our scenarios. So the red here is our high scenario, again, with the shaded range representing the 10th to 90th percentile of our model ensemble. So where most models have their results, with the solid line representing the median. And same thing for green there. That's our moderate scenario with the shaded range and the median. Another thing I'll point out here is the orange line that's kind of jumping back and forth all over the place over the gray. That is actual gridded historical data as well from sort of the NUSplin product that's overlaid right on here as well. Mentioning that because I pulled a few insights from that for looking at interpreting some of our precipitation variables, I should say. So a lot of great information that's immediately accessible coming right out of some fantastic data sources. So I mentioned all of that as context for some of the actual analysis of precipitation projections that I thought would be interesting. So we'll dig into some climate model data, talk a little bit about what it means. So I actually ended up cutting this section down a little bit at the last minute, but I've left three variables here that we'll talk through in turn that show different types of trends. I just wanted to unpack a little bit what some of the climate data is telling us. So with wet days, ice days, and total precipitation, we'll look a little bit at how often we get precipitation, what type of precipitation we get, and how much precipitation we get, which I think are pretty common questions when we're looking at these types of variables in a climate change context. So we'll start with wet days here. And first, I'm going to lay out what's being shown on this slide because I have crammed quite a bit of information into it. On the left-hand side of the slide, I have some information from that gridded historical data. So this is actual on-the-ground weather station observations that have been interpolated onto a grid. And looking at sort of the entire length of what was available historically, I wanted to pull some statistics around the mean and the standard deviation, so quantifying the amount of variation around the mean for each of these variables. So for wet days here, which are just the days where a millimeter or more of precipitation falls, typically in this location, which is Halifax, we would see around 160 days per year would be our median amount of wet days. And looking at our standard deviation, it's pretty common for that to vary by about 12 days. That's our standard deviation. So below that, I've included the sort of 1 standard deviation and 2 standard deviation range, being the really trying to depict most years fall within 1 standard deviation. So it's very typical for us to see as few as 148 or as much as 172 days. Anything within that range is very normal for Halifax. And almost all years will fall within 2 standard deviations. So that 136 to 184 days, we won't see out towards the end quite as much, but we'll see them sometimes. And then very rarely we'll see an outlier even beyond 2 standard deviations away. So fewer than 136 days or more than 185 wet days. We'll see those once in a while, but quite rarely. And I'll come back to why I have laid that out in just a second. The chart that I'm showing on the rest of the slide is showing some other things. This is looking at some of the climate model data. So this is for CMIP6, our latest version of climate modeling, for 4 different periods of time, 4 different 30-year periods, with 1981 to 2010 in the first column there representing our recent past, 2011 to 2040 representing the period we're in now, some of the changes we've already started to see, 2041 to 2070 representing the middle of the century, and 2071 to 2100 representing the end of the century. And for each of those time periods, I've shown information for 2 scenarios. SSP2 4.5 is our moderate scenario, looking towards the future, and SSP5 8.5 is our high scenario, looking towards the future. And for each of those, I've shown the median value as well as the range of the climate model results, as well as the trend that we might see within them. And we're starting with a look at wet days because, frankly, there's not a whole lot here to look at with the climate information. We can see that the median values are really not changing very much over time. Maybe a kind of a 1% increase or decrease depending on the period, but certainly not a consistent trend over time that we'd be interested in. The range of values from our climate model outputs are within a pretty constrained plus or minus 4 or 5 days or so. And frankly, that's all just pretty normal. If we compare that sort of value to the gridded historical value, even looking at sort of the most extreme case of take our 156 days plus or minus 6 days, highest scenario, furthest out in time, if our average wet days under that set of conditions is 150 days or 162 days, if we're counting for that plus or minus 6, that's still very much within our 1 standard deviation range of what was normal historically. So looking at a variable like this, we can conclude that, at least for this location, climate change is not having an appreciable impact on how frequently we get precipitation. So that was a lot of numbers to look at to come to that rather simple conclusion, but I think it's useful to, again, just put these changes in context with what we've seen historically. So if that was an example of a variable where we're not seeing much of a climate trend, let's look at one where we're seeing a rather extreme climate trend. In this case, I'm looking at ice days. And this is not directly a precipitation variable, but I think the state of precipitation on the landscape is of interest to many folks in terms of whether it's frozen or liquid. So ice days is really just looking at days where the temperature is staying below zero for the entire day. So this is where snow and ice is not melting. Ice is potentially growing in rivers and streams and things like that. That's a nice day. Looking at our gridded historical data on the left, we can see that we would typically get a median of about 41 ice days per year here in the Halifax area, and we'd see a standard deviation of about 9 days or so. So anything in that sort of 50 or 32, pardon me, to 50-day range would be quite normal historically, and on sort of rarer occasions, we might see something in the 23 to 59-day range if we're looking 2 standard deviations away. And if we start to compare that to some of the climate model data, we can certainly see some larger impacts. Looking at our median values for our moderate scenario, that's changing quite quickly from that median of 41 historically to 30 in the period that we're in now. That's already 11 fewer days where ice might be forming and persisting. 23 days by middle of the century, 15 days by the end of the century. And under our high scenario, SSP 5 8.5, that's even more dramatic. We sort of get to that same level by mid-century and as few as 7 days or so by the end of the century. So looking at our percentage change, that's 63% decrease under our moderate scenario and 83% decrease in ice days under our high scenario. Looking at our range of model results, there are some models there that are showing as few as, if we're looking at 7 minus 6, that's as few as 1 ice day per year under at least one model that's showing that as a possibility. Again, under a very high scenario far in the future, but just useful to keep that in mind. And comparing some of these values to our typical range historically, we can see that even in the period that we're in now, that 2011 through 2040, that median value of 28 or 30 days, that's already lower than our lower bound of our 1 standard deviation range of 32. So a typical year now is already abnormal looking at our historical kind of value. And as we move towards the middle of the century, that's already getting below our 2 standard deviations outlier as far as a really unusually ice day free year. And towards the end of the century, that's just absolutely insane in terms of the amount of change. So conclusion for this location, climate change is making sub-zero days significantly less likely. And of course, that will have implications for some of the water resources work that we're doing. Final one here, looking at a more moderate trend in a variable, the amount of precipitation that we get. Here I'm looking at total precipitation. I'm looking at this annually. Again, we could break this down seasonally or do a variety of other things, but this is a useful place to start. Looking at our gridded historical data, we'd see around 1,500 millimeters of precipitation as a typical amount historically, with a standard deviation of around 175 millimeters. So again, keeping that in mind, precipitation amounts in this location vary quite a bit from year to year. It would be quite normal for us to see anywhere from 1,325 to 1,675 millimeters within that 1 standard deviation range, and absolutely do see years, at least relatively regularly, within that 2 standard deviation range, 1150 to 1850. And this one's sort of interesting because we're seeing some of the trends in the climate data falling in different places within that standard deviation range. So looking at our median values, first of all, we're certainly seeing a trend towards an increased amount of precipitation over time. But again, remember, we're looking at 30-year averages. So if we're looking at the period that we're in now, a 4% or maybe 6% increase in total precipitation in a typical year, or maybe around 10% towards the middle of the century, we know that there are some years that are going to be a lot higher than that, some years a lot lower than that. This is just kind of teasing out that climate trend again. But we start to see, it's really towards the middle of the century where those types of values are getting towards the higher end of our 1 standard deviation range of what was normal historically. Like that might start to get a little bit more noticeable, that sort of thing. But certainly knowing that our precipitation varies quite a bit from year to year might disguise some of these trends for a while. So really being prepared for, again, how much precipitation varies from year to year remains the most important thing. But underlying that, we do have this increasing trend as well that's useful to be aware of. So that's a little bit about interpreting some climate data related variables for precipitation. I wanted to add a section here in as well around IDF data, so really looking at extreme precipitation, because I know this is of interest to many folks. So we'll touch briefly on this for a few slides here. So first of all, IDF curves, if you're not familiar with this term, intensity, duration, frequency curves, are really an attempt to relate short duration rainfall intensity with its frequency of occurrence. So this is where we get, if you hear of a 1 in 100 year rainfall event or something like that, it's because we're looking at historical data, analyzing what was statistically likely, and trying to tease out how frequently certain intensities of rainfall would happen. Uh, yes, which is all that the rest of that is saying. I will move on. So in terms of interpreting IDF curves, there's a few limitations that I wanted to point out right ahead of time before we get to an example of looking at some interpretation. And I'll devote a slide to each of these, but just to list them quickly. First of all, keeping in mind the quality of historical data that we're using to generate IDF curves. Second, looking at precipitation events rather than flooding events. And third, thinking about the impact of climate change on extreme precipitation specifically. In terms of the quality of historical data, there's one specific example that I'm working up to talking about, but I think this sets the scene for it nicely. What I wanted to mention here is that IDF curves are very station-based, meaning that the values in an IDF curve highly depend on what exact amount of precipitation was experienced at a specific location during its historical record. In the Halifax area, which is again where I'm located, there are 3 IDF stations that you might find yourself referring to. I'm not sure if you can see my cursor here on the top right, but there's a station here around Halifax downtown. There's a station up here around Halifax International Airport, and there's a station down here around Shearwater. And the interesting thing about looking at the IDF values from these 3 stations is how much they differ from each other. If we look at the Halifax International Airport IDF curve, their 1 in 100 year 24-hour events, it's around 141 millimeters. For Shearwater, we see a similar value, around 146 millimeters. But if we look at the Halifax IDF curve, which is sort of between the two, we see a much different value of around 233. And that's sort of interesting in the fact that if you were just to, the Halifax station, the reason why it's so different, it was the only one that was in operation for 2 major historical events in this region. 1942, there was a torrential rainfall event. 1971, Hurricane Beth. Both had 220 millimeters or so falling in 24 hours, and that was caught at the Halifax station. Not at the other ones, either because they weren't in operation yet, or just the localized nature of that precipitation wasn't quite captured there. And that's really interesting for interpreting return periods and things like that, because this area experienced another rainfall event of this magnitude in 2023, which I'll talk about in just a minute here. And if someone were just to look at the IDF data from, for example, the Halifax Airport or the Shearwater Station, they would be missing the fact that this area has now seen 3 rainfall events of this magnitude in the past 85 years or so. So anytime we're looking at return periods, it's really important to make that in reference to a specific station. And ideally, it's best to review data from several nearby stations to understand to what extent they vary, because there may be different reasons to prioritize different stations. For example, if there was some sort of topographical or meteorological reasons why that precipitation event that happened in Halifax couldn't happen at those other 2 stations, that's important to know. In this case, it just happened to be in operation and capture those events, so it couldn't be accounted for in the others. But really, that local historical context can be really important for interpreting the results. And another challenge with some of the older rainfall data is that a lot of the observations were only recorded once per day. So we don't necessarily even have the data to calculate sub-daily rainfall rates from some of those major historical events, like the 42 and the 73 that I mentioned. So while we can still certainly compare the 24-hour totals, we don't always have a robust historical data set to analyze some of the sub-daily extreme events. That'll become clear as I move into an example in just a minute here. Second, just briefly pointing out the difference between a sort of precipitation event and a flooding event. There is a difference between a 1 in 100 year rainfall event and what we think of as a 1 in 100 year flooding event. We can look at extreme precipitation mostly from a meteorological lens, but if we want to relate this to an actual flood, we also need to think about hydrology. We need to think about antecedent watershed conditions. So for example, is the ground saturated? Is it frozen? That has a major impact on how that amount of precipitation actually moves across the landscape. So again, when we're thinking about talking about return periods, it can be helpful to be clear on what exactly we're considering. And in this case, I'm only considering rainfall events, not sort of the runoff and flooding components. And then finally here, in terms of a limitation or another consideration, really thinking about climate change, because as the climate is warming, um, that warmer air holds more moisture and can lead to more intense, more extreme rainfall events. So current guidance from Environment and Climate Change Canada is to use a temperature scaling methodology to account for climate change in IDF curves. Really, this relates to the fact that sort of this physical relationship that precipitation intensity increases by around 7% or so for every degree increase in sort of our climatological temperature. Um, so this approach gives us quite a simple, powerful, physically justifiable approach to adjusting our IDF curves to account for climate change. And all hundreds of climate change adjusted IDF curves for stations across the country are available again on climatedata.ca. It's a great approach for understanding that impact. And the reason I've spent so much time talking about these limitations is I wanted to briefly walk you through an example of a major rainfall event here in Nova Scotia and talk about how we can interpret that information in the context of return periods and climate change. So to take you back about a year and a half ago now, in July 21st and 22nd, 2023, we had a major rainfall event in Nova Scotia. So as a result of a tropical air mass, a slow-moving trough of low pressure, there was really just torrential rain and thunderstorms across relatively broad areas of central Nova Scotia. In some areas, we had more than 200 millimeters of rain falling in less than 24 hours. Localized reports were as high as 260 millimeters falling, which was quite high. A couple of other statistics there. One station had 163 millimeters falling in 6 hours. There were some stations that had 1 hour rainfall rates of up to 100 millimeters, things like that. And really, the impact of this event was at least close to catastrophic. There was a province-wide state of emergency, evacuation orders, numerous roads were impassable, bridges washed out, things like that. And again, in this case, thinking about the flood event that was exacerbated by saturated ground. So we're going to kind of put that aside in terms of the actual flood event and the response to it and all of that, but we can at least analyze the rainfall event in terms of how common or how rare this type of rainfall event would be for this location. So what I've done here is carrying over those statistics that I mentioned on the last slide around the 24-hour, the 6-hour, and the 1-hour amounts that were reported at weather stations in the region, and really trying to tease out what was the actual return period of this event. So I've looked at, or I've pulled 3 different IDF curves for the Halifax station. Again, this was the station that's had the best representation of historical extreme events. And I've looked at the historical IDF curve, so just looking at the historical data. I've looked at the near future sort of period that we're in now, the 2021 to 2050 region, and I've looked at an end of century IDF curve for I scenario just to see how our interpretation can vary depending on what IDF curve we might be looking at. Starting with our historical amount, we can see that 24-hour total of 200 millimeters or so, pardon me, was not unprecedented. As I mentioned, we have seen events in this magnitude before. Based on this IDF curve, what's circled in red there, it's probably around a 1 in 50-year event for the locations that got around 200 millimeters of rainfall or so. The locations that got up to 260, that seems to be sort of off the charts rarer than a 1 in 100 year events. And the same thing for the 6-hour and 1-hour duration totals there. Those are beyond what we would consider a 1 in 100 year event, just looking at our historical IDF curve. The reason why it's important to start building in the climate change piece here is that that story starts to change as we look into the future. Looking even at our near future IDF curve, that's sort of 2021 to 2050 period, we can see that that 200 millimeter amount in 24 hours is actually even more common than it was historically. That's probably only like a 1 in 25 year events looking at our next couple of decades here. And that isolated reports of, up to 260, that's actually a 1 in 100 year event now. That's no longer off the charts rare, something we can't necessarily plan for. That's something we should probably start thinking about designing infrastructure around, for example. For those really extreme 6-hour and 1-hour events, those are still off the chart at this point. But as we move even further, we can start to see that change as well. So looking at our end of century IDF curve, realize that's labeled incorrectly. That's actually a 2071 to 2100. I'll update that for the slides. But this is our highest scenario furthest in the future. We can see that under this set of conditions, that 200 millimeter event is actually even more common now. That's potentially a 1 in 10 year event at this location. That 264 millimeters that was off the charts rare looking at our historical IDF curve, that could be as high as a 1 in 25 year event under this set of conditions. So much different than things were historically. Our new 1 in 100 year event under this set of conditions could be as high as 336 in this scenario. That's wild. Our 6 hour total here, which was 163 millimeters, which was again off the charts rare looking at historical data, that starts to be within the realm of possibility for the 1 in 100 year events, looking towards the end of the century under that high scenario as well. So things like that, we can start to tease out some of those interesting interpretations of events. Really, under all scenarios, the likelihood of extreme rainfall events is increasing as we move further in time. Things like that 1 hour, 100 millimeter is still really rare looking at what we have here. Again, I might want to be thinking back to the prior major historical events that we had. Did we actually capture the rainfall rates there that we needed to understand how rare this is, or was this truly such a substantial outlier, for example? But these are the types of questions we can start to ask and answer as we move forward with that kind of analysis. Looking at the time here, I do want to leave a bit of time for questions, so I'll briefly touch on some of what I had planned around choosing climate data, just because I think this is a nice place to leave us off. So I've thrown a lot of data and different considerations at you already. You might be wondering, this all sounds great, but Alex, how on earth do I actually choose what data I should be using for a certain purpose that I have in mind? There's a few questions that I encourage you to think through as you're considering that question. The first of these is the context. What are the actual goals or desired outcomes of using data? Are you just trying to use it for communicating a concept, communicating a general climate change trend? Are you trying to make a decision around operational decision making? Are you trying to identify adaptation priorities? Are you trying to be really rigorous in terms of engineering design or developing a policy? All of those different contexts might lead you to selecting a different type of climate change data using different scenarios, different percentiles, things like that. Looking at the climate variable of interest, do projections exist for it? What about other types of data? Are there historical trends that we can look at, like I was doing with the gridded data, for example? Not just looking at the climate change information, but trying to understand how unusual or how typical year-to-year variability happens, things like that. Is there local or expert knowledge that you can take advantage of to interpret historical or future events, for example? For the timeline, we have seen, or you may have noticed here, that a lot of the scenarios that we're looking at are quite similar until around mid-century or so. But the further we look into the future, that becomes a larger source of uncertainty. That choice of scenario has a larger impact. Really thinking through the consequences of the choice that we're making. Again, thinking about how much risk is present, to who, to what, from an undetectable level of risk to a risk that we can see but we're able to adapt to severe and irreversible. Thinking about our risk tolerance. If we're looking at, just picking an example, putting in a culvert to manage stormwater, the types of climate data that we're looking at might be very different if that culvert is on a road, a major access road to a hospital that we never want to be washed out, compared to if it's on a secondary access road that's sort of little used. We might still want to understand the climate data in those ways, but what we're actually using for design might be quite different. Thinking about, are we interested in what's likely, or are we interested in the extremes of what's plausible? So again, there's different choices we can make around scenarios, around what models are in our ensemble, what percentiles of the model that we're looking at, and all of those could be appropriate depending on what we're trying to do. But those are all choices that we can make. And if you're looking at existing sources of information, understanding the choices others have made helps you understand if those are appropriate for the purpose. And finally, really just thinking about whether the choice of data is feasible. In the real world, we have budgets, we have materials constraints, we have space constraints, we have buy-in constraints from the public or from decision makers. Again, we can't design everything for the highest possible rainfall events, looking at our highest scenario furthest into the future. We just don't have the funding, the space, the materials to do that. But understanding the information about climate change can at least help us identify what places we should be using climate data and how to use that most effectively. And really, it's about trying to document and justify your decisions to build transparency, build trust with folks around how you have used climate data for your purposes. Hopefully that was somewhat comprehensible. Very briefly, I'll just end with a summary slide here around kind of the 6 different things I tried to briefly cover in our webinar here today. First of all, again, if you take nothing else away from this, climate services organizations are here to help or to point you in the right direction for assistance. If any of this sounds interesting, but I covered it too quickly, or you want to dive into the details a little bit more, reach out to someone who can help you. That would be a great takeaway from a session like this. Second, we talked about some of the key concepts. So I just wanted to make the point that understanding some of those key concepts does really help to support accurate and clear communication when we're using climate data in our work. Third, I showed a little bit how data portals like climatedata.ca, among others, offer a wealth of freely accessible information. So if you're avoiding using climate data because you aren't sure how to find it or think that you might have to pay for it, there's a ton of information out there as a starting point. I'd encourage you to dig into it. Fourth, we looked at how analyzing trends in precipitation variables can support decision making for a few different common variables. And again, there's many more out there as well. Fifth, we had a brief chat about how climate change adjusted IDF curves can provide some really useful insights into extreme rainfall. And then finally, we just briefly talked about how we can select appropriate climate data for the purpose that we had in mind. So that was already a lot of ground to cover, but I think we've got a few minutes left for questions. I'll leave my contact information on the screen here, but I'll turn things back over to the Watersheds Canada team if there's a couple questions that we can cover here. Thanks, everyone.
Awesome. Thank you so much, Alex, for fitting in so much information and also making sure to explain all of it thoroughly. We had a couple comments sent to us about how people have used CLIMAtlantic's information in the past and also just how you presented today and how it was really easy to follow. So I really appreciate you as a presenter. We do have a couple of submitted questions, and I'll do my best to try and match when they came in. So the first one I think was when you were going through those three examples with the tables and the data. And so the person is asking if the data used, if it's raw or if it's gone through some sort of quality assurance, quality control process. If so, what procedures do you use?
Fantastic question. So yes, it has gone through a process. So just to kind of briefly describe what's happened here, we have the climate models at the global level that have put out their results for things like temperature and precipitation. That information has been downscaled to an even more local spatial resolution for Canada by some of the organizations that I mentioned earlier. And it has been bias correction process as part of that and things like that. So yes, that has happened. No, I did not have to do it because that already has happened as part of this process. So again, if you're accessing data like this, I was literally looking at some of the charts. Like for example, I'll just scroll up to this guy. I was looking at charts like this, scrolling across and just pulling numbers directly off of it. All of the hard stuff has already been done. I can just look at the actual results and start using that for analysis. Great question. But yes, it's easier than it has ever been to use that sort of information.
Great. And I should mention that a lot of the kind of links or main organizations that you've mentioned during your presentation will be included in that one-page handout that we're giving everyone. So like Alex said, if you just scroll down something fast enough or you just want to have it that you can take to your coworkers or post somewhere on a Lake Association website or anything like that, that handout will come with the recording in a follow-up email to everyone who registered. And before we run completely out of time, I do want to say that one of our staff members is going to put in an anonymous link for a survey. So if you can give Alex and I some feedback about today's presentation and also any topics or speakers you would like to see in future webinars, that would be a really helpful spot to do that. The next question we have is about the 1 in 100 or 1 in 200 year precipitation events and how those events are often not taken into account for when doing infrastructure planning. So the question is it a concern that our interpretation of extreme events are based too heavily on historical data and not looking at future models enough? So if we're not improving our policy adaptation to climate change fast enough because we're looking at that historical data more than future models.
Great question. Yes, that is absolutely a concern. We don't want to be designing infrastructure for a climate that doesn't exist anymore, we're only getting further away from what was normal historically, of course. The good news is I think there is action happening on that front. I think it is more commonly becoming best practice to use climate change information for designing some of that infrastructure, things like bridges and culverts, stormwater infrastructure, that sort of thing. I think there's still a lot of work to do on that front, particularly for many, more local municipalities, for example, that don't necessarily have the technical capability to understand some of these things. There's still some learning happening on that front. Engineering associations are still getting word out to their members, that sort of thing. There's still decisions to be made on, even if you decide to account for climate change, what the actual standard is for that. That might be set at different jurisdictional levels over, are we looking at the 1 in 100 year events under a certain scenario or a certain percentile of that scenario at a certain period in the future? Those are all decisions that have a very real impact on budget and materials and all those other things that I mentioned, which is where that feasibility piece comes in. So yes, it should be accounted for. Great to see that more people are doing it. I think we still have a ways to go. If you're interested in diving into that a bit more or looking for advice on how to do that, again, that's a great place to connect with climate services organizations to understand what might be appropriate for your context.
Great. And then the next question is an add-on. So just in case you want to say anything else, someone's saying that they believe the standard for a plan is a 5-year storm for new infrastructure like stormwater management. And so they are wondering if you have any suggestions or opinions what we should be planning for instead.
Again, that's really context dependent. It's a great question. But I think that goes back to why was 1 in 5 years design storm the prior standard? Why, like, was that for insurance purposes for a new building? If so, do we want to maintain that 1 in 5 year standard, but look to a future 1 in 5 year storm and what that would look like? Or are we already running into challenges around that not being enough and we want to potentially design to a higher standard? And again, that might be different for typical non-critical infrastructure versus critical infrastructure. That might be different for an industrial facility where the consequences of a leak would be environmentally catastrophic versus, a secondary road that floods and we're fine, or a park or a trail or something like that. All of these things should factor into our decision on what climate data is most appropriate for the context. So keep those things in mind as you're trying to make that decision. As in the absence of guidance from a legislative or professional body. Yes.
Great. We have two more questions, so I think we can just get through them really quickly here.
Sure. Yeah. Happy to stick around
Someone's
for a minute.
wondering about like volunteer opportunities or how they can get involved with CLIMAtlantic. The question originally was submitted about submitting data to the databases, but obviously that's a much higher level.
Mhm.
So they're wondering if so I'll just extend the question to how can I get involved with CLIMAtlantic if they believe in the work and they want to be spreading the message and getting their community involved. Are there ways that they can reach out and do that?
Yeah, fantastic question. So, a few different things come to mind, depending on what level of involvement you're looking for. At the very least, I'd suggest signing up for our monthly newsletters. There's a ton of great information about events that are coming up across all 4 provinces, funding opportunities that are coming out, new data and resources that are available that we're highlighting on a regular basis. So if you just want to sort of stay informed on what's happening, that's a great place to do that. Each of the 4 provinces, and here in Atlantic Canada, we have set up climate adaptation communities of practice in various different ways. So if you're interested in coming out to events and chatting with fellow practitioners or interested citizens a couple of times a year, virtually or in person, there's some opportunities to do that and connect with folks. Yeah, those are probably the best ways to stay connected, and various opportunities comes up. We don't necessarily have a volunteer program or anything like that, but if you're interested in chatting about data or how your organization might be able to take advantage of services, would always encourage folks to reach out and connect. We can chat through those possibilities.
Okay, awesome. And then somewhere in your presentation, you must have mentioned a toolkit. A coastal toolkit is what it says here. And so someone was just wondering about more information for that. They're a shoreline property owner and want to learn more about what they can do.
Amazing. Yeah, I briefly mentioned it. It's probably a full presentation in its own, but just to kind of briefly describe where to find it and what it is, you can find the Coastal Adaptation Toolkit on CLIMAtlantic's website. There's a menu on the top that says Tools. It's in the drop down there. The Coastal Adaptation Toolkit is really intended to help coastal property owners in Atlantic Canada specifically, though it might be applicable elsewhere depending on your shoreline. Understand what their options are, what their best options are for addressing coastal flooding or erosion risks. So really answering, it's a sort of a decision support tool. So an online questionnaire, you would answer a few questions around what type of erosion you're experiencing or what type of flooding you're experiencing, some of the characteristics of your property, like how exposed to waves it is, what the makeup of the shoreline is, and it will do a bunch of calculations on the back end and identify maybe this is a really good site for a living shoreline or for whatever else, right? Just to kind of make that professional advice a lot more sorry, I should say it's not professional advice, but it helps to try and make that type of advice a lot more accessible rather than needing to hire a professional to come in to do a site assessment as your first step. This might at least help you understand what types of options are a good fit for your property so you can find an appropriate person to connect with. So a lot more to say about that, but there's a ton of information on the website and you can certainly reach out to our team with specific questions.
Amazing. Got through it all. Thank you again so much, Alex, for your time and your expertise. We'll be sending everyone the follow-up information, including Alex's contact information. So if you think of a question afterwards, you'll have a way to reach out to him. And we'll be sure to send out all of that in a follow-up email later this week for everyone. And everything you get from us, the two of us, is free to disperse to anyone that you think would benefit from it. Really great conversation starters with the handout and some of the resources we'll link out to for a topic that can sometimes seem very overwhelming and hard to figure out your first steps. And so I'm just really thankful for organizations like CLIMAtlantic and people like you, Alex, who are helping bridge that knowledge and action for people so they can take steps in their own community. So with that, we'll say thank you everyone for tuning in, and we'll see you maybe in a few weeks for our next Freshwater Stewardship Community webinar on March 6th.